Okay. So, in the last lecture, I discussed with you genetic algorithms. Among other things, I told you that genetic algorithms are typically not very efficient, and they are not even guaranteed. And I criticized genetic algorithms in several ways, yet I tried to teach you so that you know what is this thing about which a lot of people are very positive and a lot of people are very negative. Okay? So, you should know what it is, how does it work. And I also told you that in my own career, I implemented genetic algorithm once. Basically, my student did, and I suggested that he does it. And that was in 2001, 2002, and that was when I had not developed the proper multimodal optimization method, and that student had to solve a multimodal optimization problem, or a problem that was formulated as a multimodal optimization problem. Okay. So, now this was done in 2001, 2002, and then I formulated the real proper multimodal optimization method in 2004, and unfortunately, that stayed just like that for a number of years, because that was done by an MTech student, and that was an idea at the spur of a moment, and I gave that problem to her and gave that method to her. To begin with, I sat with her to code the initial program, and beyond a point I left it in her hand to continue, and she did a good job. But then after finishing her MTech thesis, she left, and after that I felt that in order to communicate, I needed to conduct a lot of brushing up of that. Okay. So, for the want of that brushing up, that work remained unknown for a long time, and much later a PhD student, the same Vivek Mehta, who did this work in the penalty method, he polished this method, this program, and then we published it. Okay. So, the published result is here in the paper, which you can go through. It is very nicely and simply written, because Vivek was a good researcher. He is a good researcher. Okay. So, he is still in academics and doing well, and Divya is in ISRO according to the last information. So, this method we named as recursive perturbation approach for multimodal optimization. You can go through this detailed thing at your leisure properly, and if necessary you can implement it, and in your implementation, as usual, you can vary the details a little, and still it will work. It is expected to work. Okay. And what I will do here is I will outline a summary to you. Okay. So, recursive perturbation approach to multimodal optimization, REPAMO. Now, this method follows the philosophy of growth and colonization of a large landscape by human beings. So, the original inhabitants of any large landscape were some tribes, whatever, and they must have started from a very small number, and now they are a huge population and colonizing a large area, right. So, take our South Indian plateau. So, there how do you think a small population started colonizing the area and grew in population and settled down throughout the Indian peninsula, okay, South India, entire South India Deccan plateau. So, in the plateau, in the entire landscape, there are lots and lots of hilltops and lots and lots of valleys. So, people typically look for the valleys and settle down there. So, how did they start? How must have they started? Okay. So, originally they must have come from somewhere and looked for a suitable valley minimum point, okay, and settled there. And after some time, after a few generations of human beings, when they found that that little valley is not enough for sustenance of all these people, I am assuming that they were farming and doing animal husbandry. So, when that land area of that valley was not sufficient, certainly they did not expect that the hilltops around will be nice place to settle down. Still, search parties must have started from that valley and looking for other valleys. The purpose is to find minima, right, but then looking for other valleys, I am expecting that those people were intelligent, okay, certainly, and so they must have gone to the nearest hilltops from where they can see what are the valleys around. Okay. So, now from this valley they must have perturbed in several directions and headed for the close by hilltops. And these search parties, I am not telling that this was necessarily a process of organized colonization, might be at a later stage it must have been, but to begin with they must have found that they are not in a position to get their livelihoods in this valley anymore. So, they have to look for new land, or some of them might have left because they fought with the population there. Okay. So, they went in small parties, went to the hilltops, and from the hilltops they must have surveyed around in all directions and seen which way nice looking valleys they see. And from there, if they suppose the search party was some 30 people strong, then from each of them, from that each of the hilltop, out of those 30 people, they must have separated out in groups of, in pilot groups, reconnaissance groups of 2 or 3, the mission of whom was to go to one nearest valley and survey it and come back and tell these people at the top what is there. Till that time these people at the top will be camping. Okay. Then they must have gone to the nearest valleys. One set of 2 surveyors must have gone to one valley, another set must have gone to the another valley, and if they were algorithmically working, or if they had lost the bearing of the original valley from where they had come up, then one search party would go there also. Okay. On the way, if they lose the direction, fine. So, they will go there and then come back and say, sorry boss, we went to the same old colony, okay, no good. But others would have discovered new valleys, and then to some of these valleys these people would go and settle down. Okay. And knowing that some people from the original valley also would come up and settle there, fine. In time, in another century or 2, these valleys also will be saturated, and then this process will be repeated. So, this is the philosophy that we propose and implement in RIPAMO. Okay. So, how does the algorithm work? Exactly as I have told you, you select a starting point x naught and set generation number 0, and then minimize the objective function subject to constraints whatever it is. Okay. Record this x star, the minimum point, as the root node of a tree. That means, you are going to save all the minima and all the maxima also as a tree in the data structure of a tree. Okay. So, this is what you would have got then. I am writing x star as each of these nodes, because each of them will be some sort of extrema. Okay. So, this is an x star and this is a minimum. Okay. So, this is generation 0. Now, from here you decide on a number of directions. Okay. So, actually not directions, you decide on a number of perturbed starting points. So, basically this is the recursion. Okay. So, this is the recursion. That means, from inside this entire process, this entire procedure, this entire method will be called again from inside. That means, a branch of this same thing will be started from inside and going deeper and deeper. Okay. So, recursion is a standard technique in numerical analysis in programming, and most of the languages support it. Okay. So, you have a function, and from inside the function you call that function once more. And why should people do it? If you get that kind of a thought, then I will tell you one very simple mathematical example in which recursion is the simplest and most crisp method of evaluating a function. You think of factorial. What is factorial n? Factorial n is mathematically defined as n times n minus 1 times n minus 2 times finally going up to 1. Okay. So, this is the mathematical definition of factorial. Now, how do you write a function for this factorial in your programming language? You can simply define factorial n as one if n equal to 1, otherwise n times factorial n minus 1. A neat way of defining this, right. So, if you want to evaluate factorial of 6, you will call it with n equal to 6. This will turn out to be false, and you will come here, then you will have to evaluate 6 times factorial of 5, and then the same function will be called again, and then in place of this factorial 5, it will be put n equal to 5, and then this will be false, this will be true, and that will evaluate as 5 times factorial of 4, and this will go on. Finally, inside deepest, when it will be called with n equal to 1, then this will be true and it will come out. As it comes out, then that will be inserted here in the upper one, and then that will come out, and so on, like everything will come out one by one, and finally you will get here 6 times 5 factorial. That means 6 times 5 times 4 factorial, 6 times 5 times 4 times 3 factorial, that is this, and then step, and then it will come out, and it will give you 120. So, this is the typical kind of call for a recursion. Okay. So, something of that sort will be done here. So, first round you start with x naught, set 0 generation, minimize f x, record x star at the root node, okay. And then you start the recursion. That is, in the recursion, what will be the part and parcel, what will be the body of the recursion? You perturb the current x star in a number of directions for multiple starting points. You see, for all these new journeys, you are not taking this itself as the starting point, because taking this itself as the starting point may not be very good. Why? Because if this is a local extremum, then this will satisfy the first order necessary condition. In particular, if it is an intermediate point, then right now you will not get any direction in which will operate as a descent direction, right. Even if it is a constraint optimization problem and it is a boundary point, then whatever direction qualifies as a descent direction, that will not be feasible. So, using this as a starting point may turn out to be useless, because you will not get any descent feasible direction. That is why it is necessary to perturb a little, and that perturbation needs to be not extremely small, not infinitesimally small, then it will not be of great use. It should be somewhat sensible, not too large, it will be small, but not infinitesimally small. So, substantial perturbation, fine. So, as you perturb x star in several directions, you get several new starting points. Now, from these starting points, if you again try to look for minima or extremum of the same kind that x star itself is, then you will end up at the old one itself almost with guarantee. Okay. So, that is not a good idea. So, now you better go to hilltops, not to valleys. So, do not even seek a valley, seek hilltops from these perturbed points. Okay. So, from each of the starting points, these starting points, increment g, that is, if the original was 0, then now it becomes 1, and then minimize not this small f x, but it is negative. You see, minus 1 to the power 1. By incrementing g, you have made it odd. Okay. So, now it will be minus f x. Basically, now you will be maximizing, looking for hilltops. Okay. So, you do that and you get a new extremum. I am calling extremum because it will be minimum of capital F and minimum or maximum of small f, depending upon what is g. Okay. So, if the point x star that you have got is the x star that you have got now, if that is a new extremum, if you did not have any record of that earlier in your tree, then record this as a child node. I am noting it as x star minus, because this is going to be a maximum in this particular generation, g is 1. Okay. And then you conduct a recursion deeper. Okay. So, that means, if it is a new extremum, then from here you will conduct a recursion deeper, and then you will get another x star. If that is also a new extremum, which it is likely to be, then you conduct recursion deeper. Like this, and perhaps this turns out to be the same as the old one. So, this gets stopped, and in that case, else. First of all, if it is not a new extremum, then you come out of the recursion one generation higher. That means, if it is stopped, then it is not recorded. It is not recorded, and you come out here. From here, now you have the other perturbed point. Along that, you go like this. Perhaps it is new. Okay. So, you go deeper, and this will go on happening. You go inside, and then if it stops, great, actually not great, actually bad, because that means you did not get any more fertile directions from there. Okay. And as long as you go on, you go deeper and deeper, and then as you come out, you end up coming out and then trying the next one. And so on. Okay. So, after a while, you will find that you have grown a large tree if the function has a large number of minima and maxima. Okay. At the end, all these nodes are blocked because they were not new. Okay. And that is it. Okay. So, from each of the starting points, perturbed points, you increment g odd to even to odd, minimize this function, which basically means minimize or maximize depending upon g. Okay. And if new extremum, then you record that new extremum as a child node and you go deeper, else you come out of the recursion one generation higher and proceed to the next perturbed point. At the end of it, test all the collected nodes in the solution tree for minima, maxima and saddle points. Now, you will ask from where the saddle point business came? It comes because in some iterations, in some generations, rather than getting a minimum or maximum as you expect, you actually end up at a saddle point, and that is to an extent inevitable, because it may happen that the function has the function has less number of minima and many more maxima, okay, or other way around, that is possible. For example, on a plane you think of a function which has a minimum at the center, okay, or say maximum at the center, and around it there are some 12 extrema of the other kind, and beyond that near the boundary there may be the other extrema of the central kind. Okay, so, that kind of a possibility is there. So, if you have this kind of a situation that you have got a minimum point surrounded by a large number of maximum points, so, this is the complete feature of the function. Okay. So, one minimum surrounded by 1, 2, 3, 4, 5, 6, 7 maxima. In such a situation, what may happen? So, from this minimum, as you go to these maxima, say suppose in the first round you go to 3 of these maxima, you reach 3 of these maxima, this one, this one, this one. So, this is generation 0, this is generation 1, this is generation 1, this is generation 1. Okay. Now, how do you think the contours will be in this locality? You see, from minimum to maximum the contours are one way, from maximum to maximum the contours will be like this, like this, like this, like this, and then like this. There will be a saddle point here. Okay. So, from here as you perturb in several directions and you look for new minima, one of that journey, one of those journeys would get stuck here, okay, because here it will certainly notice that it might. Okay. So, it might get to this saddle point and mistake it for minimum point, and this kind of thing happens. We have seen such a thing happening. So, that is why at the end it is important to test all the collected nodes in the tree with the optimality criteria, okay, optimality conditions, and thereby decide them as minima, maxima and saddle points. And in this process you would have got a large number of minima which you wanted, and if you can make this process of exploration sufficiently detailed, then you will have the confidence of declaring that you have found all the minima. For example, take the case of our standard South India with which we started. Do you think that in entire South Indian peninsula there is a single valley which has not been explored till now? So, the exploration has been detailed, sufficiently detailed, and therefore, I think whatever valleys are there in South India, they have been located, they have been found, and if habitable, they have been inhabited. So, you would know that you have found all the local minima, and among all the local minima, if wanted by comparison, you can then easily identify or global extrema, global minima. That is, as in South India, you can say that which of the points, which are the places which are at the least height from the mean sea level. You can certainly say that, right. So, this is the algorithm. Now, some details. Perturbation directions. How many directions you should take? How many perturbed points you should take from each of these local extrema? One possibility is that take all the coordinate directions, plus x 1, minus x 1, plus x 2, minus x 2, and so on. So, these will give you 2n new starting points. Besides them, you can take the eigen directions. What are the eigen directions? What you can do is that at each of these x star points, I am taking this x star point as an interior point, need not be. So, if they are not interior points, then some of the new starting points you will not get, as simple as that. But if it is an interior point, then at that point the first order necessary condition will be that gradient equal to 0. So, all the first order derivatives will be 0, which is fine, and then you can work out this, right. And as you determine this Hessian will be a symmetric matrix, and therefore, you can have its eigenvectors as an orthonormal family of eigenvectors. So, you can say that these will be our additional directions in which we will perturb. Makes sense? So, these will be another 2n directions. Why that makes sense? Because along the eigenvectors, along one eigen direction, you will expect the function to change fastest. In the other eigen direction, you will expect it to change slowest. So, it will be a good idea to include both of these. Basically, the directions along which you expect it to move fast, change fast, that will be a good direction, and then symmetrically, if you want it to be sufficient exploration, then you would take the orthogonal other directions also. So, that will be another 2n directions, and then you may ask for some random directions in addition. So, another 2m directions maybe. Now, as long as random directions are concerned, there is no limit for that matter, and how detailed exploration you want to do and how much computational effort you are ready to spend, that will determine what is m. In our implementation, we used 2n and this also 2n. So, 6n directions we chose, coordinate directions, eigen directions and random directions. Later we felt that perhaps it is the random directions which will be good enough, and you can decide what policy you use in your implementation. And one more thing, the native method to minimize this function, that is minimize or maximize f x depending upon what is the generation number, that can be any favorite method of yours. So, if it is unconstrained problem, then decide your favorite optimization method. If it is a constrained problem, then you decide your favorite constrained optimization method applicable in this kind of a problem. And there are some details, some here, some here. So, depending upon your knowledge, your understanding of the objective function and constraints, you can determine what native method you choose and how many directions and which directions you choose. So, all these things are implementation details. Okay. So, just as a little sample, I will show you some of the solutions that we found. Unfortunately, in plots we can I can show you only the 2D cases, okay, the 2 variable cases, because other things cannot be plotted. So, and here the description of the algorithm in very clear, crisp technical terms you will find, okay, including the parameter values. This was the illustration. Okay. So, this is the algorithm. Implementation details, yes. So, this is a function called the 6 hump camel function. Starting from this point, which has been taken just like that, one minimum you come to. This is the root node. From here, perturbations were made and maxima were sought. This interior maximum and these 3 boundary maxima were found. Incidentally, the starting point which happened to be a boundary maximum. Okay. And then in the next round, here we called this as the generation 1, this as a generation 2, this as a generation 3 and so on. In today's outline, I have taken this as a generation 0 actually, okay, and then 1, 2, 3. Okay. So, then from this maximum, these 2 new minima were found. It is possible that one of the older minima were found, not recorded separately. From this maximum, this was another new minimum found. From this maximum, this and this minimum were found. And in the next generation, maxima seeking generation, you see these has become the new starting points. This one, this one, this one and this one, and several new extrema were found here. Like this, the collection in the tree are developed. So, in a way this is also evolutionary, okay, and generation by generation it collects more and more solutions, but here the difference from genetic algorithm is that at every new generation stops with the identification of a few fresh extrema, minima or maxima depending upon which generation. Okay. So, this is the full set of solutions of 6 hump camel function together. This is the case for Himmelblau function, okay, which has 4 minima. This is Gillen-Hills function. You see several minima and maxima have been found in several generations, and this function has a large number of maxima minima distributed in a little uneven manner, more rare here in this locality and here lots and lots of extrema near these 2 boundaries. Okay. You see, I took the analogy, I took the metaphor of South Indian peninsula, right, a hilly landscape, and where you have a lot of hilltops and a lot of valleys. This is actually an example of like that, Gillen-Hills. So, lots of hills and lots of valleys. Rastrigin's function is one great function which gives you many such extrema. Okay. So, you can see from the contours that the minima and maxima appear at very even distribution, but the optimizing algorithm does not know that, right, it has to find it. This is Ackley's path function. This is also almost regular appearance of minima maxima. Then we worked with higher dimensional functions also. In particular, Rastrigin's function can be developed in many dimensions. So, we tried from 3 dimension to 8 dimensions, and these are the statistics of number of minima, number of functions, and in how many generations and how many solutions we found. You see, in all cases we have found all the solution. This algorithm has found all the solutions, and that means that our exploration strategy was sort of sufficient. Now, this was a constrained Himmelblau function, that is, now the domain is on this boundary, on not boundary, on this curve. That means, Himmelblau function with an equality constraint. Okay. So, equality constraint has been shown in by this dashed line. So, these are the minima and maxima. So, from here it goes here, and from here it goes here, and so on. Then we solved one inverse kinematics problem in robotics. The robotics inverse kinematics problem of standard open chain robots is known to have a large number of solutions. Okay. So, we tried to find out all those solutions, and we modeled a solution as a minimum of a basically least square kind of an objective function we formulated, and we found its solution. Okay. This is constrained Gillen-Hills. Okay. And robot inverse kinematics is constrained because there may be joint limits. So, when we went to compare RIPAMO, we found that standard genetic algorithm was no choice. Only two algorithms we found which came anywhere close to the performance of RIPAMO so far as effectiveness and efficiency were concerned. One was an algorithm called clearing algorithm, okay, and the other one was called ASMAGO, and with these also we made comparisons for over those benchmark problems for which they had given their answers, in which they have given some results of their algorithmic runs. So, this is a comparison of RIPAMO with clearing, and when you study it, you will find that our method is more efficient. So, this is RIPAMO, and it will be interesting if some of you in the long run or in the short run itself implement it and share with the class what was your observations. Okay. So, this completes our discussion on multimodal optimization, and in one or two more lectures I will summarize some points of the remaining advanced topics, but in which we will not spend too much time except for variational calculus, for which the lecture is actually already there. All right. Okay. Thank you.